No one left yet, which is great. So we're going to kind of take a small detour into steady state modeling. Pretty much everything we've spoken about thus far has been dynamic modeling, transient stability modeling. Those are the models you're putting into the software. You're studying time-based things, over a period of time, what's happening. But the really important piece of IBR modeling that is just not a consideration really whatsoever for the synchronous world is aggregating your plant. So where a synchronous machine is just small cables, short cables, one transformer, two transformers, relatively few elements. A wind farm or IBR plant specifically has many inverters, different collector system sizes, lengths, auxiliary equipment, tie lines. They also have main power transformers and things like that. So the topic of aggregation is extremely contentious, and it's really hard for a number of reasons, right? The main reason is that when you're doing like an actual planning study, or when you're submitting your model for interconnection planning to the utility, you're submitting an aggregated model, right? And that aggregated model is usually, one main power transformer or two, depending on how your plant is, or a couple, right? One actual machine for each technology type, and one step-up transformer. So very few elements when compared to all of the hundreds of elements that are at an actual IBR plant. And the reason for that is that the softwares right now just have bus limitations, right? Their limitations are getting less, right? They're expanding the number of buses that you can have in a simulation study, especially positive sequence. But just a couple of years ago, we were butting up against literally the limits of buses in the case, especially when you have a case like the Eastern Interconnection, right? You're doing a study case, and the Eastern Interconnection is every machine, every piece of equipment, every element in the case. It was actually such that when we were putting together the system-wide cases, we would actually delete a lot of things we were turning off, right, to get rid of buses in the software because we're up against the limit, which means that if we're up against the limit with aggregated models only, we're certainly not going to be able to do each of the IBR plants in their entirety, right? Because now instead of 10 elements at an aggregated plant, we have hundreds and hundreds, maybe 200 or so, 100 elements in that. There are buses and things in an actual disaggregated plant. So there's the question is, why should I ever make a disaggregated model when I'm never going to use it again in the actual study process and planning process? Well, I think a very important piece of developing and interconnecting a plant is actually doing a design evaluation before you get into doing those transmission studies, interconnection studies. So they can be very good for tuning your own site, testing your own site, ensuring things don't go wrong in the future once you connect it, like real in the ground connect it. And it can also be really good economically and for design evaluating the entire plant. So talked about it, and I'm going to pick numbers and Andrew will fix numbers. But the difference when you're, I guess we'll talk about, step back a second. So the difference between an aggregated disaggregated model representation as far as flows through the point of interconnection, it varies pretty significantly between a BESS or a PV, where a battery energy storage or a PV plant has a pretty small collector system, relatively small collector system. So you may not see a huge difference between an aggregated and disaggregated PV plant, maybe a megavar, 1-2 megawatts, something like that. So not too big of a deal, right? But that could also have, if you're making this facility and you're right up against a power factor requirement of the utility, that could be expensive, right? 1 or 2 MVARs of cap at your site could be expensive. It may be cheaper to do a study like this. But when we talk about the wind, right, a wind farm with a large collector system, sometimes miles long feeders, especially with a lot of wind where because those long feeders are there, the difference between the voltage at your point of interconnection after it goes to the step-up transformer and after it goes down the whole collector system, you might have significant voltage drop or voltage gain. And I'll pick a number that got pulled out of 2800 because no one liked my number, but you may see about 10% difference. Is that reasonable? Okay, I'll get a shrug in there. That's perfect. So maybe 10% difference, right? So if you look at feeder 5 or collector feeder 1 on the top, the first IBR unit, that could be 0.98 per unit voltage. The one at the end might be 0.88 voltage, right? Those are very different voltages. One of them at the end of the feeder is in the ride-through mode, and the other one isn't. That's very different. when you're trying to study these things as a whole there. The other consideration is a lot of these technologies, or some of these technologies, are voltage dependent. So if your voltage is right at unity, 1 per unit, you have a pretty good reactive power curve, right? It's, there are technologies where even if the voltage kind of strays a little bit, 5% either way, you still get the full capability, right? For winds, a lot of times after you get close to 5% and go towards, ride through, in the normal operation range at 10% range, you get degraded reactive power capability as your voltage gets worse in one way or the other. So you may have, for example, that example I said before, if I'll change it a little bit since we're not in ride through anymore, but if it's 0.91 at the longest farthest away turbine, that turbine has a significantly different reactive power capability than the one right next to the substation, which means that it's probably significantly less reactive power capability. So if you're studying your facility in an aggregated model only, and it's a large wind farm, you may see, when you do your, say, reactive power capability testing to show what your capability is to meet those 9.5 requirements, 9.5 power factor requirements, you may pass that in the aggregate pretty easy, right? It'll be good. But then when you go to connect your facility, if they're actually testing it in the real world, like in ERCOT, when they make you test and ramp and show your capability, because those drops, because there's reactive power voltage dependent reactive powers, you're short by significant margin. So once you've gotten that far, the solutions aren't cheap at that point. The solutions, are anywhere. What I've done for these, and maybe you've probably done the same, is you can either go and tap each do a detailed study and tap different transformers, step up transformers, the unit transformers on the collectors differently throughout the plant, so they all kind of are about the same for the same reactive power capability. That has a huge impact on fault ride through, because now the taps are all different throughout the plant, so they're all going to see different different voltage gains and drops. You could also just add more capacitors at the point of interconnection or at your substation bus, which is expensive and hard to do very quickly. So it's a lot of the times good idea to do a disaggregated design evaluation study in the positive sequence domain or in the steady state domain. I'm not going to recommend a full detailed or disaggregated model in the EMT right now, because not everyone has Andrew supercomputers for that, but it is possible.
Yeah, can I just make some opinions about that?
You may make.
So since I don't have, Alex is right that aggregation is contentious right now, especially in the EMT community, but they're not here, and so I get to say whatever I want. So you get my opinion on this. My opinion is that, like Alex said, it's very important to know about this effect, that especially for wind. Solar and batteries is not so much, but for wind, where you have these long collector systems, you can get this voltage drop effect, and it can be material for your capability at the point of interconnection. It can also be material for something we call partial ride through. So if you're having a fault at the point of interconnection or somewhere out in the system, the voltage goes to some sort of threshold level and causes some of your plant to trip and not other of it. That's a real thing. It's a non-starter for EMT and even for phasor domain studies, maybe phasor domain studies, but for EMT is not the right approach right now, for two reasons. One is disaggregated models first of all, EMT is already a burden for a lot of people. It's not super easy to do. It's not bad, but we're working on it, right? Everybody's trying to get up to speed with EMT. If you add disaggregated stuff in here, my goodness, you're going to be in a world of hurt, okay, with EMT. It's really, really a major burden on the EMT study. Looking at a single model by itself is going to be a burden. If you start adding, now we're modeling 20, 30, 50, 200 IBR plants into the same simulation model. If you want to disaggregate them all, good luck with that, right? It's just not going to happen. So there's a practical problem with disaggregation in EMT for grid studies.
What is a normal laptop, one disaggregated plant, say 100 turbines?
Yeah, I mean, it depends on the size of the plant.
Yeah, so 100, how long would that take to run?
It's not going to run on a normal laptop.
Yeah, okay, exactly, yeah.
So you're going to need a powerful computer. And that's just for one plant. So why are you doing this for one plant in EMT? The second thing is, this idea of partial tripping is real, But when we're moving to grid studies, we're actually interested in, if you're thinking about IEEE compliance, 2000 compliance and all that, partial tripping is important. It's talked about. But because of these practical constraints, we can sort of put that on the back burner and say we're really interested in a lot of tripping. A little bit of tripping is important, technically a violation, all of that stuff. If you're really interested in it, go and do a special study on it, but focus on the big picture for now. That's my opinion. And the reason why I wanted to just make sure that you've all thought about it and heard my opinion is because we're starting to see, I would say, slightly misguided criteria. So some utilities are now extremely anxious to get on top of all of these things that Alex is talking about. And so they're very well intentioned. But if they're hearing this message that we need to disaggregate all the EMT models, they start to ask all the developers for disaggregated EMT models. Now everybody's got to be making disaggregated EMT models, and we can't even use them in our studies. So it's something we have to collectively push a little bit back on right now. Maybe in the future we're able to get there, but right now is not the time. So we have to push back on those types of standards, in my opinion.
No, that's a good opinion. The other piece of that is the things I just talked about, partial tripping because of voltage drops, reactive capability because of voltage drops. You don't need EMT to study that. You can do that in the steady state. You can do that in kind of a pseudo steady state if you're using like Power Factory or something like that. And you can do it with a transient model if you really want to. And the difference between, I would do it, that's my opinion, but the difference between computation from a aggregated to a disaggregated EMT is infinite orders of magnitude, right? But the difference between an aggregate run, 20-second aggregate run for an IBR plant and a 20-second disaggregate run for an IBR plant is 5 seconds to 15 to 30 seconds, right? Depending on the manufacturer's model and their code there. So that's not a huge difference to study the whole thing in the disaggregate. And that's the kind of positive sequence phasor domain is where this is important. You do not need to do EMT at all in a disaggregate. You may not even be able to. And the things we're looking for aren't able to be studied. The only kind of caveat would be like, I'm not even going to say that actually. I'll start a whole different thing. But power quality and harmonics is another thing. But special study, yeah. Yep. All right, so this little red box here this would basically, so this would be a disaggregated plant. Red box is pretty much the elements that would be included in an aggregate plant. Obviously significantly simplified, but we talked about all those reasons there. I think we already talked about all of this. Let me make sure. Oh, the second one. It's not as hard as it sounds. I lost a lot of arguments in the IEEE world because a lot of folks are under the impression that making a disaggregated steady state model or a disaggregated phasor domain model is this very difficult thing to do. But how do you all make an aggregated model when you do it based on drawings? You're taking the drawings, you're putting all of those elements into a spreadsheet or a code or a tool, and you're turning that, then the tool does the math and makes it aggregate, right? So you're already doing all of the steps to make a disaggregated model. You're just not putting one out, right? You're not spitting one out from your code. So when I was in the consulting world, it was the same exact process for aggregate or disaggregate. You had a tool where you put in all the elements and cables and junction boxes and transformers and all those things, and then they just stitched them together in a disaggregated model, and then you followed like was IEEE's guidance or whatever guidance you want for the method of aggregation. So really it sounds like it would be a really hard thing to do to make this full detailed IBR model for just a couple of studies. But really the extra effort is very minimal, right? It's just the extra effort is I added in my code to spit out that one model, and then I just run them. I solve them both side by side and make sure they're about similar. And when I say about similar, within the errors we talked about before, because they're not going to be perfect there. So huge thing to know. None of the folks who argued with me are here, so I can say that too. So you're doing the same work either way. And then also, Andrew hit on it, the simulation domain, the study purpose matters. You don't need to do a full disaggregated model for certain studies, but the main ones would be reactive power capability, partial tripping. Because if you're missing partial tripping, and that's outside of those NERC disturbances, the majority of disturbances are partial tripping for wind specifically. And partial tripping is why they're not showing up as a reportable NERC event. So it's a very important thing, happens all the time. We're missing it. We're going to continue to miss it in the planning stage, but kind of studying it on your own side or in the design evaluation interconnection study phase will let you know if your site is prone to it. Some wind farms based on their collector system and the cables used or whatever equipment they put in there, maybe they had an old transformer from 10 years ago they got to throw somewhere. That could be a huge difference in partial tripping where, more modern, even from the same developer, same manufacturer, much less prone to partial tripping. So what you're trying to study, what your site looks like in the domain you're trying to study in, all have huge effects on whether or not you need to do aggregation or disaggregation. I'm not saying you need to disaggregate everything, but I used to disaggregate most everything, especially for like NERC PRC24, which is now PRC29 for IVRs, because it shows partial tripping, and it's still a violation there. Let's see. I already said all of this. Okay. So just to visualize what we're saying, or what we've been saying, is the dotted line is NERC's no trip boundary. This comes from a really good report from NERC about this. This came from Rich Bauer, the event analysis, because of partial tripping. So the partial tripping observations drove this type of analysis, and their words are, it can be observed that there are a difference in voltage drop between two extreme IBR units can be significant, which is a really wishy-washy say that it's very different throughout the system, even in a collector system. So the dotted line is the no trip boundary, and you can see that the two lowest drops, so the blue and the yellow, which is lowest and highest. Sorry, lowest is blue, highest is red, and the yellow is the aggregate. They're all different voltages throughout the plant. So and some are on one side of the trip curve and some are on the other side of the trip curve. So it just goes to show that you graphically, when they do the math in an example system, that this type of thing, some are going to trip, some aren't going to trip, and you'll see that throughout. This is the same thing on the other side. And then we're going to get into kind of a fun painting thing here to talk about generic and standard libraries as a visualization here. So this also goes back to what I mentioned before, right? I don't have a problem personally with generic or standard library models. It's just whatever you need to consider, same way as aggregation, what you're studying and why you're studying it and what you're trying to get out of it. So first example is, the task, right? We have a task. So this would be represent an IBR plant in general. So the example here, the anecdote is to paint a vehicle, just a vehicle. It's got wheels, it moves. And this would be kind of a forward-looking research-based study. I want to make sure there's a wind farm here, a solar farm there, battery energy storage here. And you have two palettes, two painting palettes, right? The generic or standard library palette is this kind of cartoony. You get like 6 colors, very simple watercolor palette. You can probably draw a vehicle with it, but there's not a lot of colors here, not a lot of detail, not a lot of fine lines, that type of thing. And on the other side is equipment-specific models, right? So you have every paint color. You have all the colors, you have a mixing board, you can mix them together, you can make whatever you want out of it. So if you're just trying to paint a picture of a vehicle, you can probably paint that with both those palettes, right? Very simple car. You can paint them with generic or equipment specific. So when you're trying to do these types of things, like representing a simple plant or representing a simple control mode, like for voltage control or primary frequency response in most cases, say you simplified the ramp rates and gains on a equipment specific model, you can get a pretty good representation, right? And this here, specifically this example, is part of the reason why even NERC validated plants from mod 26 and 27 still were involved in all those events and still tripped offline. So this is kind of it feeds into the misconceptions about modeling, because if I'm thinking about just making an IBR, they're both pretty good. They both have their own use. So the second is a van, right? So it's not just a vehicle, it's a van. A little bit more detail, but this is basically represented an IBR plant of a specific type. So not even a manufacturer, just this is a wind farm type example, and you're going to struggle to make this level of detail with the simple palette on the left, right? You can probably get the wheels right, you can probably get the body right, but you're missing a lot of significant detail there. So the gap between those two is smaller than between a real product, but still you're having trouble with this easy palette, even to make a slightly more specific equipment type. And the last is a Mercedes sedan. I don't own one, but if anyone wants to sponsor me because of the slide, I'll take it. But this is an example of like a specific type of plant in a specific manufacturer, right? And if you want that, you're painting a very specific picture, which means you need all the colors in the toolbox. And it's not going to paint this with the generic palette. So really easy kind of thought example with pretty colors, since we're halfway through this course, and sometimes it's nice. But just to kind of hammer it home, right? It's very different. It's good to see in the visual, but you're losing detail as you get more specific, and you really need that detail if you want to actually represent what you're trying to. So this is an example. I don't know how easy that is to see out there, but when I was at Vestas, we spun up this study to kind of put some real world data to this. So what we did was we worked with the utility or the ISOs. We took the models. We got the models for each site from the planning model, the actual planning model for TPL compliance. We compared that to the actual models being used from the manufacturer or from the developer. And the first piece there was zero matches, zero correct matches, was the balance of plant data. So that's BOP data on the left, which is wild, right? Because balance of plant should be the easiest thing to model, right? It's cables in the ground, you have cut sheets, you have drawings, that should be pretty great, right? But none of them are correct. The kind of nuance here is that a lot of the mismatch was things like on-load tap changers, either not operating in active mode, or wrong dead bands, wrong step sizes, wrong step numbers. Those are kind of the main sources of mismatch. That and like supplemental devices like caps, capacitor banks and inductors and things like that. So the other kind of jarring one is protection settings. Not a single one of the protection settings matched in the planning model to the product. This is a little bit in the nuance as well. And the nuance here, and this is probably a Vestas and a couple other manufacturers specific problem, is that when you have a generic model, if you guys use generic models, they're discrete protections, right? So all you can do is make a step function. I can say at this voltage and this time I trip offline, at that voltage that time I trip offline. But a lot of manufacturers, maybe half the manufacturers, it's a curve, like a not discrete, a linear, like a continuous curve. So you can either the joke, we were kind of sassy at a utility once when they asked us to represent one, and I gave them a generic model with I think 1,500 voltage protection settings in there. I did every millisecond basically from one to wherever we were going with protection settings, and they didn't like that very much. But that's the only way you can get close. Right? How do you represent a continuous curve at the level that we're talking about and timescales we're talking about with discrete numbers? But outside of that, there were also just wild misparameterizations, right? And that could be firmware updates, whatever, that weren't captured in the as-lefs, or a number of reasons, confusions about where protections are, that kind of thing. It gets less bleak, I guess, when we look at the easy stuff like voltage and frequency deadbands. Maybe a quarter of them are decent. I don't know if it looks like a fifth of them are pretty decent. Close out of that. But still, a lot of mismatch. And same with voltage and frequency slope. So there's a reason why these are out here. These are picked here. And these are the tools in the toolbox that the operators need in the normal operations and the abnormal operations. These are the things that should be validated for folks to use. If an event happens and the voltage and frequency deadbands are wrong, you have differences in response. If the slopes are wrong, you have differences in response. So you're not getting what you're supposed to be getting out of there, right? And there's this is an IRPS presentation I had Vestas come present at, and there's 12 other graphs like this. But this is just to show that when we're not like not nitpicking over a couple percent, right? These are in per unit on the left. Or sorry, they're not in per unit. They should be in per unit, but they're not. But you can see they're wildly different responses, right? The red is the OEM model. So at the top, you see just the test they wrote, or the test they did. All the voltages experienced at the slack or at the point of interconnection were exactly the same. Same profile at the point of interconnection. The active power for the OEM model, the manufacturer-specific model, rode through this event completely, where the standard library model momentarily cessated for many moments, like 30 seconds or so. So again, wildly different response, and you also get a wildly different reactive power response, right? So we're not talking about just, oh, it's, you got 10 megabars when you should have gotten 15. We're talking about one tripped and one didn't. And the exact opposite can happen too. Sometimes the wrong data will show you the opposite, right? So when I say that there's wrong is never conservative or optimistic, it's just wrong. It could be either one, either way. It could be either one, even at the same plant for different tests, right? You may stay online during one fault, but not the other, and vice versa. So, pretty good real world example of what's going on with these things. So, a problem we need to fix, right? And the way we fix this is from the bottom up right now, right? There's going to be no probably real regulation to go back and no one's going to say for your in-service plant unless something magic happens, go give me a user's, site-specific, user-validated real code model. But we can make some change in the interconnection process and interconnection studies by raising the floor for our own models as we're submitting them into the process, right? The more models you submit into the process that are good, the accuracy goes up just overall here. So that's how we, as a group here and as stakeholders, can help close these gaps. Why is it so important? Probably covered all of these things as well, but let's just make sure. Yeah, we're eating into the stability margin right now. We're basically, the lights are on because of fantastic operators out there and a lot of overbuilding, those quotes, overbuilding in the past. And there is some level of stability margin that all synchronous machines also provide that. But as synchronous machines are replaced by IBRs, their margin is lessening. As we're putting more resources and stress in the grid, that margin is lessening. So as the margin of stability lessens, errors are more meaningful, right? Where if in the past, if I error in one direction or the other, I got some stability margin. I'm going to stay online. The operators will fix it on their side. But as that narrows, we really need to focus on accurate representations because as the margins are shorter, the risk management equation is significantly different. So transmission enhancements are really on a much slower timescale than IVR interconnections. So if there's a problem on the system, you could spend 10 years and put transmission in there, or you may be able to solve some of that with a detailed model with actual tuning and things like that. The other thing we talked about, in addition to the easy tools, so not the easy tools, but the common tools, the PFRs, the AVRs, if we're not modeling in detail, we're never using the cool, fun, new stuff, right? We're not using the new, fun, cool features that manufacturers are coming up with and innovating with all of the time. We're stuck with only the things that are in the generic models, which is regular primary frequency response with a regular droop, voltage control with like no hysteresis or anything like that, one gain, one ramp rate. So a lot of capabilities are left off the table, and any custom solutions you can't use, right? Because you can't represent them in those types of generic modeling. Let's see. As the margin goes away, advanced features are going to be much more important. We may see as the stability margin goes away, because of maintenance or other things, the short circuit ratio or system strength at a specific plant could vary wildly, which means that either when those maintenance happen, you redo a study, or there's some features like I mentioned yesterday, where if the system strength changes, the IBR plant controllers can measure this and change their gains to be stable in both those operation points, but we'll never be able to study that without a real detailed model. Let's see. The last one's a pretty strong statement, but if we keep using bad models that no one agrees with should be used, then we're never really doing a real study. They're all wrong. And they're neither conservative or optimistic, and it's just, you're going to get false positives or false negatives, and either one of those things may be harmful to you for whatever reason, right? A false positive means you get false good response, so you get through the interconnection process quickly, but you never studied your plant. So there's a higher likelihood for curtailing or hot fixes at the end. If it was a false negative, then maybe you're delayed, or you have issues in the interconnection process, but later on you may have fixed those problems. So it all ties in together. Kind of hit on this a little bit throughout our discussion here, but what's being underutilized right now in the US? Reactive power capability, and that's because of impediments in generic models, as far as advanced controls and kind of capabilities there for aggregate and generics, and federal regulatory processes. So FERC Order 827 is miswritten. That's a fact, not an opinion. There's a typo in the error. It's literally, there's a typo right in the order. if anyone wants to file with FERC, they're asking for it. So I think MISO may have done that. But basically what the FERC order says, be within 0.95 and positive 0.95 power factor, which means you limit your power factor. So that's a big misconception, or a big miss there. So primary frequency response, again, capabilities are, you have much more capability with a manufacturer-specific model, but also FERC order 842 was a little late as far as mandating primary frequency response. So there's still a lot of facilities out there that have it but aren't using it. The others are kind of more model-based, but weak grid support features, advanced support features, advanced voltage control features, and advanced frequency control features. We're just not able to study them right now. So those are less, I guess you probably could put regulatory all the way around to enable those things, but I didn't here, just for discussion. This is the example we talked about yesterday very briefly, but this is what I just mentioned. I cut off with my graphic. But it says maintain a composite power delivery, a continuous rate of power output at the high side within the range, which is not what we want, right? With this language, if you do exactly what this language is, gives you this curve. And the slash red, like we talked about yesterday, is all the unused capability. And this is over a third of PV and BESS are operating just like this right now. And this is exactly what we talked about yesterday. Not exactly, but very close to what was one of the main drivers of the IBR failures and the Iberian disturbance. So I'm on time. So do you want to do a little intro to grid forming this morning? Okay. I'm surprised I'm on time. So all of the things we talked about so far about the changing paradigm in modeling, it's all going to get more important. Unfortunately, we're kind of building a pile of problems to deal with. But the fact of the matter is that the grid forming inverters and the grid following inverters, as far as all the problems we discussed thus far, are pretty similar, right? Software-based, power electronics-based. The difference is control code, and a little bit of, obviously, there's a difference in need for capability there too. But the grid forming inverters just add some more complexity on top of the studying and planning for grid following. And if we're having problems right now, adding more complexity on top, we're going to have more problems in the future. So it's very important to learn our lessons now as we get going, and we can enable grid forming through good processes. There's also kind of disjointed, like the regulations, disjointed incentives and requirements for grid forming technology in the U.S. And a lot of this goes back to show me you need it, basically, in a regulatory space. So it's really hard to get a tariff change that says you must install grid forming on your battery because someone will say, well, that costs money, and why should I if no one showed me I need it, right? So we've seen actually, because of this and because of there's like pretty much no guidance from FERC or NERC on grid forming right now. Some of the more ambitious ISOs and utilities have kind of put things in places that aren't the tariff, but are still binding. So that's okay, right? If you were a proponent of grid forming, you get more grid forming that way. But what also happens is you have even more disjointed requirements throughout the country, right? So very different, or it just kind of piles on here. So every battery energy storage resource that's connected without grid forming capabilities, if they have them, there's a caveat there, it costs more money. Every day you don't install grid forming or don't flip that bit, if it's that easy there, you're losing money. It costs more money to do it tomorrow than it did today. And a lot of more modern battery energy storage, it's mostly just a software change. They're shipping with the capabilities, it's just turning it on. But the important thing also is that not every single inverter-based resource needs to be grid forming. I was in a conference and I did a grid forming panel at a conference in Berlin, and we got in like a 30-minute argument about between academics and industry folks about whether or not 100% grid forming is either possible or good. And there's a long argument, so there's obviously varying opinions there. But the key consideration is if you're 100% IBR, you need something to give a reference, right? A voltage and frequency reference. If you're 100% grid forming, then everyone's trying to shove the reference at each other, right? Which means that control interactions increase significantly. So somewhere in between, probably, grid forming and grid following, a resource mix is appropriate. The people who have done studies like this in the past have shown about 30% grid forming is sufficient. But then those are small island systems like Hawaii. And I'm sure the number is going to change based on your grid and the interconnected nature of your grid and that kind of thing. So we did a comparison of complexity between synchronous and grid following, but we're going to do it again for grid following and grid forming. So grid following is immature for synchronous, and grid forming is even newer. So it's even less mature than regular grid following. They are both software and electronic, power electronic based, which is good in the sense of we can kind of think about them the same way. But that also means that they're susceptible to the same or very similar ride-through issues. So similar complexity also and difficulties with model parameters like we talked about. Similar modeling and study risks here, just more complexity. But the big thing, and I mentioned just very briefly, alluded to it, is the grid following are kind of passive elements, right? They're taking a reference, taking an angle through their PLL and deciding what to do after that. The grid forming is setting an active reference, an active grid participant. They're driving the grid forward. So when you have a lot of assertive people in the room, they're all going to yell at each other and they're going to get in an argument, and the control interaction is going to be bad. But also, if everyone's really passive in the room, nothing ever gets done, right? So that's the kind of analogy there. So some mix of both of those is how we'll keep the system there. The other kind of very important thing is grid forming is like spectrum. There's no perfect grid forming. There's a lot of kind of grid forming behaviors, some of which can actually be done with grid following. Like fast frequency response is a fast response. It may not be grid forming, but it's similar. But just to kind of go down the list here for the actual attributes of the inverters and their reliance on grid voltage here is grid following, like I mentioned, they rely on that really well-defined voltage reference, which is kind of dictates all of their controls. But the grid forming is actually actively maintaining that internal voltage and magnitude and phase angle. So dynamically, grid following, they're injecting them into the grid, or controls current injected into the grid. And it does this based on what the angle they're seeing is. Grid forming, they actually are setting the voltage, magnitude, and frequency phase. So they're the ones dictating it. Grid following, they need that PLL, the phase lock loop, or some equivalent fast control for synchronization. Grid forming does not need this, and that's how they're able to operate in those weaker systems with kind of crazy angles, really low voltage, and things like that. I should have put a box around black start, but grid following probably can't use that or possibly use that for black start. And while grid forming can, I don't know if they should, because that's my opinion, right? Like they can self-start, like a grid forming battery energy storage can help crank the path in black start, but I don't know if that's something that anyone's going to actually put into their procedures anytime soon. But they could be involved if necessary. So big difference between those two there. Low system strength, low grid strength conditions. You can make a grid following inverter operate okay in really low short circuit strengths or low system strengths, but you're really kind of doing like an advanced control study. I mean, I've tuned wind farms to be operating at 1.2, 1.25 or whatever short circuit ratio, but that's like really detailed analysis. We're changing things that the normal user isn't available, it doesn't have available to them, and it's like a really advanced control tuning. But there is still a minimum system strength there for a grid following. So on the other side, grid forming, the stable operation range is much larger, and you can do that without a minimum system strength requirement. So they can actually just operate a microgrid or an islanded grid on their own. And then the kind of deployment for each of these grid following, I mean, most everything we've connected so far is grid following. Existing standards and regulatory efforts and things like that, they're really more aligned with the concept of grid following. The grid forming, we're really only seeing it commercially available in battery energy storage right now. Some PV can do it, but there's really not a lot of experience in how they're working, how to specify them, how to write tests to specify them, what grid forming means. And even there's a consortium called Unify, which is making grid forming standard. And we added in some frequency domain things because it's a pretty good way to test grid forming. And even in the field of experts at the Unify, there's like 6 people who know what they're talking about for that specific thing. So even amongst the people who are writing these things and doing the forward-looking work, there's a lot of knowledge that needs to be shared to understand these things, and there's just not very well defined in behavior, performance, and what's needed. So, did you have a question? Yeah, go ahead. There is a list on E6's website of all the grid forming projects worldwide, and some of them are in the U.S. I don't remember exactly what they are. Do you know? You probably know a couple of them.
Yeah, that list is also changing really fast, and it's probably not complete, the one on the ESIG one at
Nope,
this
it isn't.
point. We're going to talk a lot more about grid forming. I don't know when I'm going to get a chance to, but you want to
Later.
finish up these
Yep.
slides and
Yep. Yeah, we'll get into grid forming in detail. This is a little introduction. It does say in depth, but we're introducing it. The other thing here is that there are a bunch of different ways to do grid forming. All right. I don't know if one is better than the other. I think they're just different, but you might. All right, let's start covering it later.
yeah. So I actually cut all those slides out. Grid forming is one of my, you'll probably figure out by the end of the week that this is one of my favorite topics. This is one of my favorite things is grid forming converters. So I don't want to start talking about this.
Okay.
Um,
Save it for later then. Yeah.
I think saying there's different ways is a good way to say it.
Yeah.
Yep.
Yeah, and that's kind of I mean, it's similar to for grid following, right? There's a bunch of different ways to do voltage control or frequency control. So specifying one or the other is bad, right? Because you're limiting competition or kind of sticking yourself to one. But it's similar for grid forming as well, right? If you say you must have grid forming virtual synchronous machine controls, then you're missing innovation, right? Or you're saying you must have GFM troop controls, you're doing the same thing. So it's one of those things where I think it was a bunch of slides ago that you can standardize performance and then you don't care. Give me some performance out of your point of interconnection. I don't care how you do it. Just do it and test it and prove to me that you're good to do it. Let's see. This is an operating example here. This was in Hawaii. And this is an example of how these controls are working. So very, very fast response times. This was a very, very fast and very controlled response time. So the difference between a fast response and a fast controlled response, you don't always want a fast uncontrolled response because that's not really great. But a fast controlled response is really useful for supporting the grid throughout these types of events. So this was, you probably know more about this than I do. Do you want to talk about this one?
Sure, I know
Okay.
a lot about this one. Yeah.
Yeah, go ahead.
So this is one of the first. So first of all, Hawaii was one of the first people to specify that you had to do grid forming batteries, and this is a very large plant in Hawaii. So 120 megawatts, 150 on a 1,000 megawatt peak load. So the purpose of this, so what we're planning on doing is on Wednesday, I was going to talk about grid forming earlier. We're going to move that to the end of the day on Wednesday, which is going to be, it's going to be awesome. You guys should all stay till the end of Wednesday. It's going to be really fun. But this is one of the things that you can think about grid forming. So for those who aren't going to stay to the end, we'll just give you a couple of takeaways. Grid forming is good and stable. So Alex was saying it's a fast, stable response or controlled response. Another way of saying it is it's an uncontrolled response. In that, when you put, if you think of a synchronous machine that's spinning all day long, it has a constant, since there's a big piece of spinning mass there, when you change the terminal conditions, so the electrical conditions on the terminal of the machine, the internal quantities, the voltage phasor and angle, because of that spinning mass, don't change immediately, right? The system changes very quickly, but the internal quantities can't change immediately because they're part of this physics, right? That means it's essentially, the synchronous machine provides, as soon as you change that system quantity, there's an instantaneous difference between the internal and the external quantities. That means there's an immediate change in active and reactive power flow across that impedance. And that means very, very fast, right? Fast meaning immediate. It's a physical response, but uncontrolled. You're not controlling that. It's just happening because of physics. This is exactly what's happening with a grid forming converter, is they don't do anything in their controls. So a system changes, you get a step change in voltage or a step change in angle on the system inside the grid forming converter, rather than being a very fast controller like a grid following controller to try and control their power and their reactive power. they do nothing. Okay, they just hold themselves constant, which is very easy to control. That's just saying we're not going to do anything in our controls. It's very stable. And as a result, you get a step change in output. And so that's what you see here. In this case, they're losing a bunch of generation in their system. And this is a real event. And it matches the simulation, by the way. They can see the P simulation and the measured power. So the models were excellent, but that's just because it's Hawaii and the models are always as good as they get. But when you step the generation down, the frequency in Hawaii crashes. Okay, it goes through the floor very quickly. There should be a corresponding plot of frequency here. I can probably find it if you want, but it basically, the frequency is falling extremely quickly, and proportionate to that, you can think of the angle in the system. If the frequency is crashing, the angle is moving, right? And this is just the uncontrolled response to that angle moving. So you get active power shooting up immediately like this. There's no delay, there's no PI controller, there's no controls actually acting in here. It's just doing nothing inside, and it goes up and then it comes back down. Now there's a virtual synchronous machine controller and some other things that come in to basically control the power, but you could think of this just the same way as a synchronous machine would give you that response. You get the synchronous machine response right here, and then a VSM control response here. And then what's happening here is they put a nonlinearity into the controls so that if the frequency happens to hit, I think it's 59 hertz, if it gets that low, they put a discontinuity in the controls that just is a simple if 59 hertz, add 50 megawatts. So that's what happens here. They just step in another 50 megawatts as a boost to the frequency. So, and then you level out with another synchronous machine type swing there, okay? So the takeaway, if you're not here till the end of the day tomorrow, is that grid forming controls inherently are more stable because they're not doing anything in that fast control response time. The same as a synchronous machine. So there's nothing inherently preventing you from making everything grid forming. We have a lot of caveats around that, and Alex gave some of them. The same way that synchronous machines all can work together because of the physics that's holding everything together. They're stable in the sort of small signal world. Grid forming can do the same thing, okay? And it's stable because it's not fast. The reactions are fast, but the controls are not, okay?
Perfect. Oh, go ahead.
But we'll talk a lot more about it. Yeah, so this is a battery. So this was charging, this was just the dispatch. At the time that the event happened, it was minus 60 megawatts, so it was charging. And then when the frequency moves, it goes up.
So if it was dispatched differently, it would still do the same shape if the capability was there.
Yeah, so in this case, if it's a 150 megawatt battery, if it had been dispatched at 100 discharging, it would have gone up until it hit its current limit and then stopped.
And that's, I guess, the big difference between, one of the big differences between grid forming inverter, even a BESS with extra energy, and a synchronous machine. Like you may get the overcurrent in an IBR is much less than overcurrent in a synchronous machine.
Yeah, and there's pros and cons, right? Because a synchronous machine is governed 100% by physics even after the event. So we take the good part of the synchronous machine is it responds to the change in system. It basically resists change to the system. So voltage goes down, reactive power goes up automatically. It's resisting the change. If the frequency goes down, active power goes up automatically, resisting that change. That's a synchronous machine. But the synchronous machine is not a VSM, it's an SM. So it will do the swing, right? So it will give you that energy, and then 100% of the time it will take it back. Okay, so it's going to swing like that every time until the governors can kick in and bring you back up. And it has no current limit, so it'll swing very high, and then it'll swing very low, and then it'll come back. So that may or may not be good for your system with a synchronous machine. A grid forming battery, you can say, give us that swing, and then stop there. We want that energy and hold it. Okay, so you can see this can come up and stay up because they can add in essentially grid following controls on top of that to make it give you whatever energy profile you want. So it's current limited, that's true. And sometimes that's a downside. Most of the time, it's offset by the extreme sort of benefit you can get from those controls afterwards. So
yeah, just something you said, which is important to really keep in mind, is that outside of this type of response, then they look a lot like grid following devices. Like a normal operations or normal operations, they'll look exactly the same. Could be.
no, come on. Oh, you're pushing my buttons, right? No, yeah. So since it's a physical response, you can't control that that initial change.
So that's what I was saying earlier. It's a spectrum, like the response is a spectrum. You can get some really fast controls from grid following, but for full grid forming capability, you need extra energy in these types of controls. So if you, I'm not sure if they're Unified's publishing that document in like a week. Well, it's been in a week for about 6 weeks now, but it should be about done in 2 weeks or so. And you'll see there's tiers of grid forming. But some of those tiers can be met with grid following devices with advanced tuning, like you're saying. But there are other tiers that you need these types of controls to do. So you can get a lot more grid stability benefit with advanced controls of grid following. But to go further, you need these grid forming controls.
And so Unify is doing good work. I don't want to say anything about that. That's fine. They're working hard. There's a lot of folks working on grid following devices as well, trying to make them better, trying to make we're always trying to make controls better and everything, and trying to get them into the. I don't totally agree with this sort of spectrum idea of grid forming. I feel like there is a fundamental difference between a grid forming control and a grid following control. You can blur them. You can make the grid following devices very fast. It's a little bit like if you want to make a pencil vertical, you can either like hang it from your fingers and it's just going to be vertical, or you can try and balance it on its eraser and it will be vertical, but now you're going to have to work at it to make it work. And one of them's a lot easier than the other. And so that's why I kind of just feel like just make it grid forming instead of trying to make a grid following device so hyper tuned.
Yeah, but I'm stealing that example.
What's that?
I'm stealing that example from you.
It's actually, I think it was Andy Hoke originally came up
well,
with
I'm stealing it from both of you then.
Yeah.
All right, we'll wrap up. Oh, good.
So you're not wrong. So if you operate a grid forming device at its current limit, you don't get that energy advantage, right? You can't get an under frequency response that's substantial, for example, but you do still get a small signal advantage. So what's happening in the small signal space, if you think of like the control, we're going to talk a lot about control stability this afternoon, but if you turn up the gain on a controller a bunch, it eventually goes unstable in the small signal space, right? It doesn't, not the big stuff, but just it'll start to grow. That gets solved with a grid forming converter. So even in a weak grid situation, you're adding that stability back in even without the current headroom. You miss out on some of the other advantages like a very strong frequency response, but you don't have to always have that. All of your batteries are not going to be always operating at full discharge or full charge. And so if you're just asking for this capability when you have it, that's essentially the ERCOT approach, is they're saying, if you happen to have headroom, we would like you to use it in this way. If you don't have it, fine. So in that case, they'll have to procure extra to make sure they have enough, but they have all of this sort of available capability. But you're not wrong, and you can actually pay for extra capability if you want. If you want to make a market that says, we want you to maintain headroom so we can count on your inertial response or your frequency response, you can pay for that, and that's what they did in Great Britain.
Yeah, and also that's only for under frequency events, right? The
Or
other,
over frequency if you're on a bottom
yeah,
limit.
over frequency is fine. And
Unless you're on a bottom limit.
well, yeah, I guess that's fair.
Yeah.
Well, yeah, okay.
But under frequency is what
Most
we're
of the
really
time,
worried
we'll
about.
caveat that. With Emir?
Well, just one thought about what you mentioned, and about like not having to like have that extra capacity. So like the feedback that we have received from OEMs, like the major OEMs that we work with, is they need at least like a 10% delay to be able to provide any like reforming functionality. So that's like the minimum, like the basic.
So I've heard this as well. And I'm frankly a little confused by it. It might be true for some OEMs. What we've seen in the simulation models is most inverters already have some headroom. They're not operating at full flat out. They have a little bit of headroom. For example, if you want to provide reactive power and active power at the same time, they have current headroom. That's one thing that confuses me. The other thing that confuses me is some of the inverter manufacturers are saying, we don't care what mode you operate it in. We can flip it. Right? They're not saying that. So some manufacturers are saying that and others are not. There's also, I want to be fair to the developers and the OEMs who are saying this isn't actually free. Okay? That's probably true. To say that changing it from grid forming to grid following is completely free may not be true. There might be extra engineering involved. There might be extra auxiliary equipment that they need to add. There might even be, say, 10% inverter overhead. On a battery, the inverter is not the major portion of the cost, right? It's going to be, I don't know if people have good numbers here, 5 to 10%. So if you're adding a 10% to that, maybe it's still a nominal cost or in the overall battery project. So you can weigh that against the benefit. So I think it would be fair, whether that's true or not for everybody or you could say that there is an incremental cost to it. It's not completely free upgrade for everybody.
I think the other aspect that I'm not very clear about, and not that it's being a study, is like what is the requirement on the DC side? Say if you need like any upgrades, if the DC side needs to like operate any differently or have like any extra capability to the grid forming band.
So it's a very good question. In some cases, there's no difference, we're told. There are manufacturers who have said they're not able to do a DC coupled hybrid plant that's grid forming. So if you have an energy supply like a PV plant and a battery, and a battery on the same DC bus, they have problems controlling their DC bus. And so they won't offer that product. You have to have it decoupled with separate inverters. Other manufacturers have apparently solved that and are now able to do DC coupled grid forming. So there are DC side considerations that the manufacturers have to figure out, but it's apparently solvable. Yeah. I think if you just have a regular inverter with a DC bus, there's no inherent problem with a grid forming control for the DC bus compared to grid following. It's going to be a current issue on the battery. You're not really cycling state of charge on a full battery. You're just moving the current in and out in a little bit different way. I'm told that it's not a problem for the batteries, but when you have a DC coupled hybrid system, now you have two different sources of current. That seems to be more challenging for DC control. I'm not sure exactly what the challenges are for them, but for some.
Question about headroom on inverters sometimes, and they like when we do run out and do stationary utility scale, right? So you run into situations where we're doing a reactive power capability study for the project at the POIs. You have to make a lot of assumptions, and one is low SOC on your battery bank, which is low voltage that comes through to the inverter output that makes it a low voltage. You might have an ambient temperature effect that the rating of the plant is higher than the highest level non-derated ambient temperature of the inverter. You're actually derating the inverter slightly. Then you need to have your main power transformer sometimes cascade to get the lowest number, and you still have to make the reactive power. noise, and so that's where sometimes I think they need some headroom.
Right.
Design a plan. The easy answer to solve that problem is have a couple more inverters.
Right. Right.
And then you just have horsepower to push it. Look at your plan. Don't have it marginally designed. Just have a couple more. They're not that much.
And this may be similar, but I'm not quite sure if it's an issue or not. Please help me out with this one. But if your batteries are in good forming mode, they're always active. They're always active. There's never an inactive point. So have you heard anything about lifespan?
Yeah, and when you say active, what we have to be a little careful what we mean by that, because the current in and out is going to be likely to move a little more. So you're going to have active power flow coming in and out, kind of in a relatively small range. Okay, and that one shouldn't be a problem for battery cycling, because the state of charge, if you plot the state of charge, even if you're going rail to rail for a little bit, your state of charge isn't changing on a big battery. If it was a capacitor, that would be different, but it's a battery with, hour or two storage, state of charge is flat through that. And that's apparently what the batteries don't like, is if you're moving your state of charge all the time. Yeah. Yeah. I guess one other thing I'll just say is that the incremental cost discussion, I gave you an anecdote yesterday where developers are actually turning on grid forming without being required to do it or paid to do it because of the capacity advantages. So what you're doing is basically allowing yourself to operate in weaker systems. You're adding a ton of damping at subsynchronous frequencies, so you're basically solving your SSCI problems just without doing any control tuning or any work. And you're basically making your whole plant just a little more stable. So, it would be nice if you got paid for it as well. Of course, you're going to ask for that. But why wouldn't you also just do it? Because it's probably just going to help you work better. Another case in point is this, about 3 weeks ago, we had an event in a region that is currently forbidding grid forming. Okay, so we've done a bunch of studies. We did some for ESIG. We've done a ton in Hawaii and Australia and other places where we're showing, using these real code models, that it's working well. They're not unstable. They're very stable. And what happened in this one region is that there was a large plant, let's say 200 megawatts. It wasn't 200 megawatts, but let's say 200 megawatts. And it starts to oscillate in the real system. The operator shut them off because they're unstable. We got the models, did a detailed study. We showed the oscillation. We showed if you turn grid forming on, first of all, we did some short circuit work to show that this is actually a weak system. You didn't think it was, but it is. And so that's why you're unstable. You basically are hitting small signal control limits. It's unstable. Turn the grid forming on, solved. Everything's flat. But not allowed in the utility to use grid forming because it's quote unquote untested. Okay, so we go back and now we go through 2 weeks of detailed control, tuning, the old fashioned stuff, trying to get extra stability margin out of these controls to, the hard way, add extra functionality to kind of tune this out. And now it's barely stable, still in grid following mode. But there's more inverters coming in, next year. So we're for sure going to see another event. But the utility refuses to turn on grid forming because it's too scary. So that's frustrating for me because we can see it in the models. It's definitely going to work.